sorry. So I'll also repeat that I want to thank the organizers and Victor for inviting me to give our results of our research about nanovesicular phospholipid carriers for nasal drug administration. And going again through the human nasal cavity, just a few words, is divided by nasal septum into halves and has a surface area of about 150 centimeters squared, a volume of about 15 milliliters, and is covered with mucus in the pH range of 5.5–6.5. We have three regions: the vestibule, we are administrating the formulation, the product, and then two important regions, the respiratory and the olfactory region. Okay, nasal delivery, well known for years and years, even hundreds of years, for local treatment for various ailments like rhinitis, congestion, infection, but much more recently, nasal delivery is used for systemic and CNS treatments using drugs with low bioavailability by the other routes. But like always, we have limitations, and the limitations are related to the penetration of molecules to the mucosa, nasal mucosa. If small lipophilic molecules are well absorbed, peptides, proteins, and even hydrophilic molecules have a low absorption. So, people, when we have problem, always people are looking how to improve the situation. And my lab, my are specialists in designing innovative carriers for improved delivery, such for the skin, for the nasal membrane, rectal, vaginal. So we found how to design a carrier that has good properties, is safe, but is improving the delivery. So in this sense, we have designed what we call soft nanovesicle or soft phospholipid nanovesicles. And these vesicles look like liposomes, but are not liposomes, because liposome is a rigid phospholipid nanovesicle, also is organized having a middle full with liquid, in general water, aqueous solution. The soft nanovesicle has altered phospholipid bilayers by using solvents. This makes a vesicle which can penetrate much better the membrane or the mucosa. Also, the structure, how you will see also later another photo, the structure is different from the structure of classic liposome. Besides our soft nanovesicles, in the literature, you will find also flexible nanovesicles, and those phospholipid vesicles are modified with surfactants. In 2009, we introduced the first phospholipid vesicle altered with ethanol for nasal drug delivery, because much earlier we introduced a soft vesicle, the etosome, for dermal delivery. But here in 2009, we have the first soft phospholipid vesicle for nasal delivery to brain and the systemic population. We have evaluated these systems in pharmacodynamic and pharmacokinetic preclinical studies. So, I will talk about 3 delivery systems or 3 nasal carrier based on subvesicular carrier, subvesicle, nanovesicles. The first one we call NDS, the second one is the phospholipid magnesium, and the third one is the NVC. The difference between them is the modifying agent. For the first one, ethanol. The second one has an element which is very characteristic, contain not only propylene glycol, which is the modifying agent, but contains magnesium. And the third one is modified by propylene glycol. All the vesicles have a range of hundreds of nanometers. And what is interesting is the difference between the addition of those phospholipids versus liposome. The difference is around 15 degrees Celsius, which is a very high difference, meaning that the lamella are interdigitated and the vesicle is soft. Now, what we did with this kind of carriers, in fact, we deliver to brain and to CNS molecules for various treatments, like all these in models. Because personally, I believe very much in seeing results, what we call pharmacodynamics, meaning results in an animal model of the disease. I like results, PK results, pharmacokinetica, but I think seeing what happens in an animal model give you an idea how the treatment could be further efficient in humans. So the treatments were for multiple sclerosis, Parkinson, pain, hot flashes, anxiety, emesis, insomnia. Just a table, sure, I'll not go into, but what you can find here, small molecule, hydrophilic molecules, lipophilic molecules, and even a peptide, oxytocin, the hormone peptide has 1 kilodalton, is a small one, is not a big one, but we have not tested only PK, but pharmacodynamic effects in animal models. So the first carrier, the NDS, which is modified with ethanol, what is characteristic, and you can see here, is not only a spherical multilamellar nanovesicle, but has the phospholipid lamella from wall to wall, which is different from liposome. And we did many studies, how I mentioned before, like one of the nice, and everything was published, one of the nice studies in mice model of multiple sclerosis, the UAE mice, and we have tested the nasal administration of drugs versus controls. And we have tested the drugs glatiramer acetate, cannabidiol, and what is interesting, the mixture of two. And in effect, if you look to this graph, where we have the clinical scores of the sickness of the mice, you can see, and 6 is the mice is died, or 0 to 1, just a small paralysis of the tail of the mice. you can see that the best results, what we want, the no scores or as possible near to zero. So this red line is the line which shows what we obtained with the nasal administration in the carrier that we designed of the combination of glatiramer acetate and cannabidiol. Not only we have seen that those scores have been very, very low, but we have seen also neuronal proliferation in the subventricular zone and subgranular zone of hippocampus. Another test we have made, it was for pain therapy using tramadol in the same carrier. And what is important to emphasize is that our pain model animal is a very harsh one. What we do, we are injected acetic acid, and the animal has what is called the rice, and more number of rice, the animal has terrible pain. And you can see here that in fact in plasma and in brain, we have excellent results by the delivery of the small molecule, is a hydrophilic small molecule, tramadol, nasally with the carrier we developed. Now, a study sheep, you need to know that this is very expensive. To carry out a study with approval of the officials on sheep is expensive, very expensive, but the results are very important. And what we have tested here, we have compared the tramadol nasal versus IV administration, and also tested the M1 metabolite, which is an active metabolite, and we have tested not only in plasma, but also in the cerebrospinal fluid, CSF. And if you look here, you can see that we have shown an absolute bioavailability, because it's versus IV, this Y is absolute, of 1 or 0.9 for tramadol nasal administration and plasma and CSF. Now, the second carrier, which is very important, we just, by the way, we have granted patent of the first one I talked about, and we have also granted patent on this phospholipid magnesium. And moreover, there is a startup which took this carrier, this platform, to work first on the application for Parkinson. And this startup is looking now for investors, like always. Now, this vesicle, what is characteristic, that has magnesium and propylene glycol, but again, look, lamella from wall to wall. Now, we have used this carrier for tramadol. I will not, maybe the time is not letting me, but what also I want to emphasize is that working with oxytocin, the peptide, small peptide, but peptide, we have excellent results. And you need to know, here we have rights, the same model, harsh model, where the rights, less rights, more analgesia. And we have a parameter which is called the maximum possible effect, MPE. Here is vice versa. If the numbers are high, meaning the results are excellent. So look here, phospholipid magnesium versus nasal water solution versus liposome nasal versus non-vesicular carrier or peros. Look at those numbers, how high they are versus all those controls. Now, improve mobility. We have an animal model which is good to work when we are doing research for Parkinson. This is in fact a reserpine-induced motor impairment of the animal. And we have seen that using nasal delivery of a drug which is on the market, pramipexole, we can reverse the immobility of the animal almost completely. We have increased animal locomotor activity by 300 versus oral treatment and completely reversed catalepsy and mice model of akinesia. And the last one is the system with propylene glycol, again the same. Lamella from wall to wall. And with this carrier, what we did, we tried to see, again, in our pain harsh model, if we can have good analgesia with drugs which are not controlled. Because if you have high pain, you need controlled drugs. So we took 3 non-controlled drugs and we get very good results in our pain mouse model. So just other 2 slides. One, sure, always we are asking ourselves, what about the safety? This is very nice, it's working good, but don't forget, you go to the nose, it's a mucosa. So we have tested the safety, and we have not, again, who tested is not me or my students. We give this to a pathological lab, and named D, a pathologist, is testing. The results are coming from them. And you can see you have here positive results with sodium lauryl sulfate, and here all the carriers, and at least the pathologist did not observe any pathological alteration. So conclusion, 1, the use of phospholipid vesicle for drug nasal delivery to brain is now a growing field of research. But not only the soft vesicles, other phospholipid vesicles, and even other carriers. So I will tell that really nasal delivery of drugs to brain or for treatment of CNS problems is very active today. I would like to emphasize the short onset of action for improved treatment outcome by using the nasal delivery. And you have seen that those carriers, at least in the test we have carried out, are safe. And thank you very much for your attention. And thank you very much.